Hello guys, this will be my second video on integral identity and U-substitutions. Um, in this video, we'll be covering the two identity on the screen, after which we would demonstrate how we can use U-substitution together with these identities to solve more complicated questions. To start, I'll be showing how you can find the solutions for these identities. So starting from the first one, we have 1 divided by the square root of a squared minus x squared dx. To find the solution of this identity, you need to do um, a substitution with a trig ratio. So we're going to substitute for x a sine theta. You might be wondering how this came about. These identities are kind of related to a right angle triangle where you have, give me one second, where you have this angle as theta. So if this is theta, this will be our opposite side. This is 90 degree. This is our adjacent side, and this is hypotenuse. We all know that the sum of the square of the opposite and adjacent side of a triangle is equal to the hypotenuse. Now, looking at what we have here, we have square root of a squared minus x squared. We want this to look like this. So what we need to do is just solve for, say, our adjacent side. So we have hypotenuse squared minus opposite side, and when we take the square root of the both side, we have hypotenuse squared, opposite squared. Now they look alike. So if we compare what we have, a squared minus x squared compared with h squared minus opposite squared, this implies that our hypotenuse is a and our opposite is x, right? Now, if you have your opposite and your hypotenuse, you can find the trig ratio, the sine of the angle given. That means sine of the angle given, we all know that is opposite over hypotenuse. In our case, it's going to be what? X over a. So if we have sine theta to be x over a, it implies that what? X is equal to a sine theta. And that's why, um, that's how this substitution came about. So to solve this question, we'll have 1 over square root of a squared minus x squared dx, right? We need to find, now we already know what x is. Our x is a sine theta. We need to find what the x is. By differentiating both sides, we have a cosine theta d theta. Therefore, we're going to substitute that into this a squared minus x squared dx. Wherever you see x, you're going to put a minus, sorry, a sine theta. So instead of having x squared here, you have a squared sine squared theta. And instead of dx here, you're going to have this a cosine theta d theta. Now, we can simplify further. This will give us, my bad. This will give us a cosine theta d theta divided by, I can factor out a squared, so I'll have 1 minus sine squared theta, right? Now, if you're familiar with your trig identity, which I will cover in some video to come, you will remember that sine squared of any angle plus cosine squared of the same angle is 1. So we want it to look like this. We can just take sine squared theta to the right hand side. So we have cosine squared theta. Okay, let me write it up there. So it implies that cosine squared theta is the same thing as 1 minus sine squared theta. Therefore, our integral of 1 divided by a squared, square root of a squared minus x squared dx becomes, from here, it becomes a cosine theta d theta divided by square root of a squared. Instead of 1 minus sine squared theta, we're going to substitute cosine squared theta. Now we can take the square root of everything underneath here. So we have a cosine theta, the theta divided by square root of a squared is a, square root of cosine squared theta is cosine theta. Everything cancels out. We'll be left with integral d theta. So it's like saying 1 d theta, this gives us theta. So the solution is theta. Now the question is, what's theta? We have to go back to our substitution. Our substitution is sine, x is equal to sine a sine theta, right? So we can divide both sides by a. It implies that what sine theta is x over a. Therefore, what theta is equal to sine inverse of x divided by a. Therefore, our solution to this identity will be square root of a squared, our identity is equal to sine inverse of x over a plus c. So that is how you get the solution for the first one. We will now solve the second one. So let me just so I would update the solution. So we have a solution here, sine inverse, that's x divided by a plus c, constant of integration. Now for the second one, we're going to do it in similar manner. So we have this, right? Dx. Now we'll go back to the same triangle, right? Now this is theta, this is 90, it doesn't look like 90, but this 90, we have x, we have the sum of these two. So I'm gonna keep this as x and this as a. It means the hypotenuse in similar manner will be square root of x squared plus a squared. Or I don't want to find, let's just leave this as h. In similar manner, if this is my adjacent, if x is my opposite, and my a is the adjacent, then the hypotenuse squared is x squared plus a squared, right? This implies that we have our opposite side of the triangle, we have our adjacent. The trig ratio that we can get with those two information will be is tan theta. Tan theta is what? Opposite over adjacent. So that means we can use the substitution a tan, not sine. A tan theta. That's the substitution we'll be using to solve this question. Now, we will replace x with a tan theta and we need to find the x. So the x is what? By differentiating both sides, we have secant squared theta because the derivative of tan theta is secant squared theta d theta. Therefore, integral 1 divided by x squared plus a squared dx is the same as the integral of 1 multiplied by a secant squared theta d theta divided by, instead of x we have a squared tan theta squared. Instead of x squared we have this plus a squared. In similar manner we can factor it, so a up here is a constant, can come out, right? We have secant squared theta the theta up here. Here we have a squared, it can come out 2 because we can factor it from both, and we have tan squared theta plus 1. If you are familiar with trig ratios, again, I'm going to be covering it like I said earlier. We have an identity that says secant squared theta is equal to tan squared theta plus 1. Therefore, our integral, the x is the same as, well, a divided by a squared is 1 over a, and then we have secant squared theta over divided by the same thing, because if we replace this with this, we have secant squared theta here also. Now this results in 1 over a integral d theta, which will give me 1 over a theta. Now going back here, but what? Tan theta is equal to x divided by a. It implies that what theta is the tan inverse of x divided by a. Therefore, in conclusion, our solution to 1 divided by x squared plus a squared dx is equal to what? 1 over divided by a tan inverse of x divided by a. So having gotten that, we will use these solutions to solve more complicated questions, or we start with simple questions and then solve one or two more complicated questions by using U-substitution. So I'm just gonna take this off and just update, or it deleted both, so I would have this solution. We had sine inverse here of x divided by a plus 1, and here we had 1 divided by a tangent inverse of x, this is plus c, x divided by a plus c. Let me rewrite this. So 1 divided by a tangent inverse of x divided by a plus c. And this is how you find these identities. Now, there are some extensions to this identity, and I would give them after, I can just add it right now. So extensions to these identities, we have a couple of extensions. The extension, and I can prove them, but I would not waste time doing that. These extensions are as follow. For the first one, the extension to this one is if you have f of x prime divided by square root of a squared minus f of x square dx, then the derivative of this will be sine inverse of f of x, sorry, not not square root of x, it should be f of x to be f of x divided by a plus c. It's just by U substitution. If you apply U substitution, this is what you get. Similarly, integral f prime of x divided by f of x squared plus a squared dx. This will give me 1 divided by a tan inverse of f of x divided by a plus c. So these are extensions that make it easy to solve complicated questions using this identity. Now, I'll just solve one or two questions. I'll solve one for the first one and then one for the second one. So say I have integral and I have integral, say, I'm just going to formulate something. If I have integral e to the x divided by square root of e to the x 2x, my bad, I mean I have to have a constant first. I have, say I have 5 here minus e to the 2x. If I have something like this, I can rewrite this to be more like this, right? So I have integral e to the x. Here I can rewrite this as square root of 5, so I can square it. So my a is square root of 5 minus e to the x all squared dx. So you see, my here, if I'm using this, my f of x, so by comparison with this, I have with this, I mean this, I have, okay, let me just write it up here. If this is the same as f prime of x divided by square root of a squared minus f of x squared, I'm comparing, so this implies that my a is square root of 5 and my f of x is what? E to the x. The question is, if I differentiate this, do I get the top? The question is, if I differentiate this, do you get what's on top there? Let's see. F prime of x is what? E to the x, which is the same as what we have up here. So yes, we can use this theorem. Since f of x prime is e to the x, which is what we have up there, then what? We can just use that to solve this. We have e to the x over square root of 5 minus e to the 2x dx is simply, we're using this expression, I mean this one, is simply sine inverse of e to the x divided by square root of 5 plus c. As simple as that. If you want to verify, you can solve it the regular way and you see if that will result into the same solution. You can use U substitution and then use the identity up here, because when you use U substitution, it's going to reduce to this identity. and that's why it gives you this. I'll solve one more question because I don't want to make my videos too long. Let me, I don't want to erase all, so I'm just gonna do this. So I'll solve one more question because some questions are not necessarily difficult, but they are not too obvious. So you have to try and relate it to what you know. And practice makes perfect. The more you practice, the better you get. You solve a lot of questions and you get better or more comfortable using all these theorems or these identities. Okay, I'm going to solve an example with the second theorem. So I have, if you have a question that says, find the integral of 1 divided by x squared plus 2x plus 10 dx. Now this question is not too obvious that one of these identities will work. The first thing you could check is you want to check if you can use partial fraction. How do you know a question can be solved using partial fraction? And I will cover that in some videos to come. If you can factor this, then you can use partial fraction. But I'm positive you cannot find partial, you can't find factors for this. One thing you can do though is complete the square. So I'm gonna do that here. So we have 1 divided by, this is x squared plus 2x. I'm gonna add the plus 10 here, and I will tell you why. How do you complete the square? If you want to complete the square of a quadratic function, you take this number here. Do you see it? It's 2 in this case. Divide it by 2 and add it. Add the square. So this number, you divide it by 2 and square it. Add it. But since this is not part of our question, we have to subtract it also. Now, by so doing, taking this, dividing it by 2, squaring it and adding it to this portion, it makes it a perfect square. Now, this whole thing can be written as 1. The x is still here, 1. Now, this whole portion is x squared plus 2x plus 1, because 2 divided by 2 is 1. 1 square is 1. X squared plus 2x plus 1 is a perfect square. You just need to take this x plus is plus 1 square. It's a perfect square. It is whatever you squared here and this number, add them together, or whatever the sign is here, add them together, because it's addition in this case, you add them together and square. If this is negative, it will be x minus whatever you square in here squared. And then this portion will be 10 minus 1, which is 9. Now, I would go through all these algebra breaks, tricks. It helps when you know what you're looking for, how to manipulate. It makes it easy to solve questions. Now, this whole thing can be written as x plus 1 squared plus square root of 9 is 3, so 3 squared dx. Now, this whole thing looks like what? It looks like this. Oh, sorry, the second one. Can you see? Now, if I'm gonna use the identity extension that I have here, it says f prime of x divided by f of x squared plus a squared. The result is 1 over a tan inverse of f of x divided by a plus c. Now, f of x is x plus 1. So let's check f prime. F prime of x is 1. And what do you have up here? 1. F prime of x should be the same as what you have at the top. And I just did it. I did it. We have f of x as x plus 1, and then f prime of x as 1, which is what we have. Since this is true, we can simply use this substitution. Another value we need is a. By comparison, our a is equal to 3. So we can conclude, therefore, integral 1 over x squared plus 2x plus 10, the x which was simplified or written in a better form by completing the square gave us this, right? The x is equal to 1 divided by 3 tangent inverse of f of x. F of x is x plus 1 divided by a, 3 plus c. You see, by knowing these identities, you can solve really complicated questions or questions that look complicated by just knowing the extensions. And the extensions are found by, combining these identities with U-substitution. I hope you enjoy this video. I will make more videos. I'll be covering different topics as the week goes. I'll try to release a video every day, and I'll try and keep all my video within 30 minutes. Thanks for watching. Please subscribe for more content. Thank you very much.